Hello? 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 Okay, it seems people can hear me. Can you see my screen? Okay, that's perfect. Okay, thanks. I'll wait for a few more minutes before I start. Okay, I think I will be starting now. Hello, everyone. My name is Kostas Biliouris. I'm currently a principal scientist at Novartis, but I'm going to present some work here that was done and completed while I was at the University of Florida as a postdoctoral associate. The title of this work is MatVPC, a user-friendly MATLAB-based tool for the simulation and the evaluation of systems pharmacology models. This is an outline of what I'm going to be presenting today. So I will first give you an introduction to quantitative systems pharmacology. Then I will discuss MatVPC and its key characteristics. I will then present 3 case studies where we used MatVPC to evaluate it against other tools that are used in pharmacological drug development, and these will be 2 PK models and 1 PD model studies, and I will briefly talk about the future direction. So traditional PK/PD models. As we all know, the PK/PD models, the traditional PK/PD models do satisfy Occam's razor. In other words, they do meet the rule of simplicity. Their contribution so far to drug development, as we all know, has been enormous, and this was beautifully described by a paper by Rick Lalonde in CPT. However, the one drug, one target approach that we have seen so far is gradually being overtaken by the multi-target, multi-pathway drug approach. And one representative example of this is clozapine, which is an antipsychotic medication that exhibits very high affinities for more than a dozen different receptors. So we see that there are drugs currently being developed that target many different targets in our body. Therefore, the traditional PK/PD models that we have been using so far may not suffice to describe the underlying complexity that these drugs associated with. We have therefore seen that our field is gradually transitioning to QSP models. Of course, we do work a lot with PK/PD models that when it comes to systems level analysis, we see that people are transitioning more to quantitative systems pharmacology models. For example, if one wants to describe the interactions in this system, which shows how the different systems interact within the body, they would probably use a quantitative systems pharmacology to do that. We also see that these QSP, the so-called QSP models, are progressively entering the regulatory arena. And one example was Natpara, which is a treatment for hypoparathyroidism. So when FDA wanted to evaluate the dosage regimen for this drug, they used an open source QSP model to evaluate these dosage regimens that have been selected. And actually using this model, FDA went back to the sponsor and told them that the dose regimen that was proposed could be further optimized. So we see how important these models can be. However, QSP models are complex, and implementing them in the traditional tools that are currently available for PK/PD models can be very challenging. Therefore, there is a need for flexible tools that are built into the QSP mainstream software, and this software could be MATLAB, Symbiology, or other QSP tools. For this, we developed MatVPC, which is a new tool for QSP models. MatVPC is a MATLAB-based tool which can be used for the simulation and the evaluation of QSP models. The reason that MatVPC is useful is that it is an all-in-one tool that integrates the following characteristics. It is publicly available in SourceForge, so everyone can access and use it. It generates automatically visual predictive checks or VPCs of QSP models. It also, unlike other software that are available in the field, generates quantified VPCs, QVPCs of QSP models, which is a different type of VPCs that was recently introduced by Post et al., and this provides a more objective assessment of model evaluation. MatVPC also offers automatic binning of data, and to do that, it is using an approach that was developed by Mark Laviel and Mark Lavelle is actually the one who contributed the automatic binning in this tool. It also offers Monte Carlo simulations and 40 graphical or methodological options that the user can modify at any time. Finally, it is a user-friendly tool, and it only requires minimum MATLAB experience by the user. Now, for those who are not familiar with the VPC, I would just like to mention that VPC is nothing but a plot that visually compares the observations with the simulated predictions. And to do that, one includes both the variability between the subjects in the model and the uncertainty of the model. And then they overlay the observations with the simulations and their respective statistics. Here is the publication that is online and related to MatVPC. So for those who are interested in knowing more about the MatVPC, they can read our publication, and the examples I'm going to discuss today are included here in this publication. So now I'm going to describe the steps that one needs to follow to use MatVPC. So the main steps that one needs to follow are three. The first one is insert your parameters and equations in MATLAB files. So one needs to insert the parameter values and their equations in MATLAB files, and this is something that one needs to do in other tools that are currently used in the field, like non-mem and monoliths. Once they do that, the second step is to simply call MatVPC by using one command in MATLAB. And in this command, one needs to provide the name of the dataset, which is a dataset very similar to the dataset that one would use in non-mem or monoliths. And also, one could provide stratification variables that would probably want to use. And these stratification variables could be the dose or the study, anything that they would like to stratify on in their dataset. So here you can see a representative command that one could type in MATLAB to just call MatVPC. Once you call MatVPC, you will get a message in MATLAB which will say, please provide the name of the model. And what you do is you simply provide a name, and MATLAB will use this, MatVPC will use this to generate a folder which will include all your output files generated by MatVPC. So the first is to provide the name of the model, and the second is to let MatVPC know whether or not you want to run simulations and generate MatVPCs, or you want to use already existing simulation files that you have generated previously with MatVPC, and you just want to change the VPC plot appearance. For example, you want to change the statistics, the confidence intervals, or the color of the curves. So here you just respond by a Y or an N. Once you complete these two steps, you move to the third step, which is modifying 40 default settings at will. So here you either don't do anything and you just leave the default settings, or you can go in and change different default settings that have been set by you from MatVPC. And these settings can include the ODE solver. So depending on whether you have a stiff or a non-stiff code model, you can modify the ODE solver. You can modify the binning type. You can have automatic binning, or you can have a manual binning where you decide the binning size. And also you can modify the color of the curves, for example. So these are the three steps that one needs to follow in order to use MatVPC. And now I'm going to move to the first case study that we implemented to evaluate MatVPC. The first case study is a 3-compartment PK model where observations were simulated in non-mem. So we generated observations in non-mem, and then we generated a model also that would describe these observations. So the characteristics of this 3-compartment PK model is a linear elimination from the central and the peripheral compartment. The dosing was single dosing, which was administered either orally or intravenously. And then we use MatVPC to stratify on the route of administration. So MatVPC will automatically generate different VPCs for the different routes of administration. And in total, we used observations for 100 subjects. So here I'm showing how one uses MATLAB files to let MatVPC what their model looks like. So similar to other tools, one needs to here insert their parameters of the model with their values. And these values are values of the model that have been either estimated elsewhere or they have been adopted from the literature or anything. MatVPC does not estimate any parameters. You just need to insert the parameters of your models. Here, you provide a vector with the omegas, and the omegas are simply the inter-individual variability of the parameters. So they provide the statistics or the distribution of a parameter, and it accounts for the inter-individual variability. Here, you provide the proportional part of the residual unexplained variability and the additive part of the residual unexplained variability. So here, actually, this is nothing but the uncertainty of your model. If you don't have an estimation for that, you just leave it blank. If you do, you then insert here the residual unexplained variability of your model. Here you define your parameters with their IIVs, with their omegas. So for example, for parameter 1, you will have K12 times an exponential of eta 2, which is the omega 2 here. And then you provide the initial conditions of your model. And here we set everything to 0. Here is the initial conditions of your ODEs. And finally, you provide the volume of each compartment here. If you don't have a volume of, the volume is not estimated, you just set it equal to 1. The next step, once you insert your model, once you insert your equations in MATLAB, is to insert, the first step is insert the parameters of the model, which is something I just showed. And now the next step is to insert the equations in the MATLAB file. So this is how we insert the equations in the MATLAB file. Here we provide the number of the ODEs, and in this case is 4 ODEs for this 3-compartment model. And here are the parameters and the equations of the model. And just keep in mind here that the names of the parameters should be consistent with the names we gave in the previous file. So here are the 3 equations, 1, 2, 3 for the 3-compartment model, and the 4th equation is for the dose. Once you do that, you call MatVPC and you get a user-friendly interface where it shows the 40 different graphical and methodological options that I mentioned before, and the user can either leave them as are or they can modify them. So these options include the number of data sets that one wants to simulate to generate the VPC. They include the type of binning that one wants to follow. It's either automatic binning or manual binning, depending on the preference of the user. Then it's the ODE solver that one wants to use, and they can change the ODE solver depending on their model. Typical ODE solvers include the ODE 45, ODE 23S, and others. Here is the simulated time beyond observations, and this is a characteristic that is used in case you want to simulate only. And What it means is that if you have observations up to one particular time point, you can use this option to simulate your model for longer times. For example, if you have observations up to 100 days and you want to simulate 120 days, you would set this equal to 0.2. So here it is asking whether or not you want to plot the observations. Here are some options that one can use to modify the colors of the curves or the percentile intervals. And here you are asked whether or not you want to plot a QVPC and the characteristics of the QVPC, like the colors of the different bars. And finally, it is asking about the arrangement of the plots, how many rows you want in the figure and how many columns you want to have in the figure. Here, it is asking whether or not you would like to replace any negative values you have in the simulations with another value, which is shown in the previous box. And finally, it is asking what is the x-axis label that you would like to have and the y-axis label that you would like. Once you decide on all these different options, you go here in the interface and you click OK. And once you click OK, you get the VPC plots automatically generated by MatVPC. So here in this slide, I'm showing the two VPCs that were automatically generated by MatVPC for compartment 2 of the model I just showed. So the y-axis shows the observations and the simulations, and the x-axis shows the time. We do not include units here because the observations were just simulated and they were not real data. So the blue dots show the observations. The red lines show the median and the 90th percentile interval, the 5th and the 95th. The black lines show the 50th and the 95th percentile intervals of the predictions of the simulations, and the shaded areas show the 90% confidence intervals of the simulation percentiles. So here, again, are the plots that were generated by MatVPC, and we did the same using PSN and Expose. And what we observed here is that the two plots are identical. The plots from MatVPC and the plots from Expose and PSN were identical. As we know, Expose and PSN are considered the golden standards with NONEM in our field, so we use these to have a type of evaluation. What other tools cannot do is generating automatically QVPCs, and this is what we did here for compartment 2. Here I'm showing the QVPCs for the same model. The y-axis shows the percentage of observations. The x-axis shows the time points. Each bar corresponds to a different time points for which we had observations. In gray, you see the observations percentage above the predicted median. In black, you see the observations percentage below the predicted median. And in red, you see the predicted median. So one uses these two VPC plots for an assessment of the distribution of observations around the predicted median. So we did that, and this gives us also another type of model evaluation. And if you look here, you will see that the black line or the simulations in the VPC plot is higher than the red line or the observations, and that's why the gray area here is shorter than the black area. On the other hand, in the second plot, the red line is on top of the black line, and therefore we see that the gray area here, or the percentage of observations above the predicted median, is larger than the percentage of observations below the predicted median. So again, QVPC is another way for one to evaluate their models. Finally, we demonstrate here for the case study 1 that one can very easily change some options in this user-friendly interface, and the options that can be changed are shown in red boxes, to generate Monte Carlo simulations of their model. So here we request no binning, we request Monte Carlo simulations. The time beyond observations will be 20%. We request not to plot the observations. That's why we have set a no here under plot observations. And then here we request different colors of the curves. When we do this, we click OK in this user-friendly interface, and we generate the simulation plots. At this point, I would just like to mention that there is no time here, there is no need for time-consuming generation of new data sets. And as the non-MEM users know, in order to generate simulations, you need to generate your own data set with the simulations that you want, which is usually time-consuming. Here, there is no need for generating this data set, and you just change these options in the user-friendly interface. You click OK, and you get these beautiful plots which show the simulations of the model over time. The y-axis shows the simulations, the x-axis shows the time. First plot corresponds to compartment 1, compartment 2, compartment 3. Here, the green lines show the 5th and the 95th percentile interval. The red line shows the median, and the shaded lines show the confidence intervals of the percentile intervals. So we show, using the case study 1, how one can generate either VPC plots or simulations of their model. So I will move a little faster now to case study 2. This was a 2-compartment PK model. The difference from the previous example was that here we have non-linear elimination from the central compartment, unlike the linear elimination we had before. We have multiple dosing, unlike the single dosing we had before, and only IV infusion administration. So here again, we insert the parameters of the model, the omegas here, the residual unexplained variability of the model. We set up the parameters here with their IIVs or their omegas. We define the initial conditions of the model. And finally, we provide the volume of each compartment of the model. Once we do that, we need to insert also the equations of our model. And here we see that our model consists of 2 equations. One is the highly nonlinear equation of the central compartment, and another one is equation 2 for the peripheral compartment. Once we do that, we get the user-friendly interface where we are asked to change any different options we want. And once we modify these options that I mentioned previously, we can have a VPC plot generated automatically by MatVPC. So here again, we see the MatVPC plot for the central compartment. The y-axis shows the observations and simulations, and the x-axis shows the time. We see here how MatVPC was able to generate this VPC to bin the data optimally and to give us an evaluation of the model. If one does the same for expose and PSN, they will get a plot that looks identical with MatVPC, and we see here that the 2 plots from MatVPC and expose PSN are interchangeable. So here is also a QVPC plot, which was automatically generated by our tool, which is something that, to my knowledge, no other tool in the field can automatically generate. And we see here how the observations are distributed above in gray and below in black, the predicted median of the model. One can also generate simulations of their model, of the model I just showed here. And here to the right, we see the simulations that one can generate for this particular model using MatVPC. In purple, you see the 50th and 95th percentile interval, whereas the shaded areas show the 90% confidence interval of the percentile interval. And finally, a third case study, which is a PD model, which is highly nonlinear and describes the body weight. It was adopted from the literature. Here we stratified on the sampling times. So we assume that we have two different studies where different sampling points were used, and we asked MatVPC to just simply separate these two studies and generate two different VPC plots. Here again, we insert the parameters of the model in this MATLAB file. In the next, we insert the equations of the model. And here, in this case, we only had one equation, which was describing the PD model. And once you do this, you generate two VPC plots automatically using MatVPC. The y-axis shows observation simulations. The x-axis shows the time. In blue, you see the observations. In green, you see the percentile intervals of the observations, whereas in black, you see the percentile intervals of the simulations. The shaded areas shows the confidence intervals of the percentile intervals of the simulations. So the reason we have two VPC plots is because we, as I mentioned, assume we have two different studies with different sampling points. Therefore, you see that the observation time points here in the top plot and in the bottom plot, you see that the sampling time points were different. In this case, we used monoliths to evaluate our model against another tool. And if one looks at monoliths and MatVPC results, they would see that the two results are identical. So this was a third study that we used with MatVPC to evaluate its functionality. Again, using our tool, we were also able to generate two VPC plots, which are considered to provide a more objective evaluation about the distribution of your observations around the median of the model. Here I'm showing the two VPC plots for our model. And these three studies, I believe, showed an evaluation of MatVPC. And these are the conclusions of this work. We do believe that MatVPC constitutes a useful addition to the computational tools that are currently utilized in quantitative systems pharmacology. The website shows that so far we have more than 500 downloads from impressively more than 30 different countries. So we see that QSP and MatVPC as well are used internationally in more than at least 30 different countries. In-house, when I was in Florida, we successfully used MatVPC to both simulate and evaluate models from different disease areas and of different complexity. And these models include models for spinal muscular atrophy with both preclinical and clinical data, systemic lupus erythematosus, again, both preclinical and clinical data, and more impressively, the human coagulation network, which is a paper we recently published. And this is a QSP model which consists of 56 equations and 180 parameters. So MatVPC was able to get this model and to easily and quickly generate the MatVPC plots for this human coagulation network model, which was indeed a very complex model with a large number of parameters and equations. So the future MatVPC versions will include prediction-corrected VPCs, where different characteristics of the data are taken into account, such as the dose or others, and then a sensitivity analysis, ideally, that can quickly be implemented when one provides the model. At this point, I would like to acknowledge Miriam Kramer, who was my supervisor at the University of Florida and the senior author in the paper of this work. Mark Laviel, who contributed, as I mentioned before, the binning, the automatic binning that comes with MatVPC, and the user can seamlessly bin their data while using MatVPC. And finally, ISOP for inviting me to give this presentation. Thank you very much for your attention, and I would be happy to address any questions you might have. So I see no questions unless I'm looking at a different place. But yeah, thank you very much again. I don't think there are any questions, but please feel free to reach out to me in case you have any questions related to MatVPC. Again, thank you for your attention.